Dr. Susmita Sarkar. Today's topic is Caley-Hamilton Theorem. The content of this topic is the statement of Caley-Hamilton Theorem, next one the characteristic polynomial and characteristic equation, next one some applications of Caley-Hamilton Theorem, and last one some related problems. Now, the statement of Caley-Hamilton Theorem. The statement of Caley-Hamilton Theorem is every square matrix satisfies its own characteristic equation. Now, we have to try to find out the characteristic equation and characteristic polynomial. To find characteristic polynomial, let A be a square matrix of order n by m. That is A equal to Aij n by n matrix, and X is a column vector of order n by 1, which is equal to x1, x2, up to xn. The eigenvector corresponding to the eigenvalue lambda. Since lambda is the eigenvalue of the eigenvector H of a square matrix A, then we know from the definition of eigenvalue and eigenvector Ax equal to lambda x, and after calculation we get A minus lambda into x equal to 0. Now this is a homogeneous equation. Now this homogeneous equation has non-trivial solution if its determinant of A minus lambda is 0. Now the left hand side of equation 2, that is determinant A minus lambda, is called characteristic polynomial, and the equation 2 is called characteristic equation of the square matrix A. Next, some applications of Caley-Hamilton theorem. First one is that we can easily find the inverse of a square non-singular matrix by using Caley-Hamilton theorem. Here is an example. First example is the use Caley-Hamilton theorem, find A inverse where A is a 2 by 2 matrix. That is A is equal to 2, 1, 3, 5. To find A inverse, first find the characteristic polynomial of A, that is determinant of A minus lambda I2. Since A is a 2 by 2 matrix, then here let I2 is a 2 by 2 identity matrix, and after calculation we get the characteristic polynomial is lambda square minus 7 lambda plus 7, and this is the characteristic polynomial, and characteristic equation of the square matrix A is lambda square minus 7 lambda plus 7 is equal to 0. Now from Caley-Hamilton theorem we know that every square matrix satisfies its characteristic equation, that is A square minus 7a plus 7i2 is equal to 0. Here 0 is the 0 matrix of order 2 by 2, and after calculation we get A inverse equal to minus 1 by 7, A minus 7i2, and now putting the values of A and I2 we get A inverse equal to 1 by 7 and 2 by 2 matrix, which is equal to 5 minus 1 minus 3, 2. Here is another application of Caley-Hamilton theorem, and we can find by using Caley-Hamilton theorem A to the power n, where A is a square matrix and n is natural number. And here is another example to find A to the power n, and the problem is use Caley-Hamilton theorem, find A to the power 50 where A equal to 1, 1, 0, 1, which is also 2 by 2 matrix. Now, the characteristic polynomial of the square matrix A is determinant of A minus lambda I2. And putting all the values of A and I2, we get the characteristic polynomial of the square matrix A is lambda square minus 2 lambda plus 1. Therefore, the characteristic equation of A is lambda square minus 2 lambda plus 1 equal to 0. And as usual, we know that the every square matrix satisfied its characteristic equation, that is a square minus 2a plus I2 equal to 0. Here 0 is the 2 by 2 identity matrix. Now a square minus a is equal to a minus I2 after simplification. Now multiplying both sides by a, we get a cube minus a square is equal to a square minus a, and also we know that from 1 a square minus a is a minus I2, and continuing this process up to 50 times, we get a to the power 50 minus a to the power 49 is equal to a minus I2. And adding all the above results, we get a to the power 50 is equal to 50a minus 49 I2. Now putting the values a and I2, we get a to the power 50 is equal to 2 by 2 matrix, and which is equal to 150, 0, 1. Next, some related problems. First problem is show that the matrix A, which is 3 by 3 matrix, satisfy its characteristic equation. To prove this, first find the characteristic polynomial of the square matrix A. And we know that the characteristic polynomial of a square matrix A is determinant of A minus lambda I. Since A is 3 by 3 matrix, then here I is I3. That is 3 by 3 identity matrix. And now putting the values of a and lambda I3, we get the characteristic polynomial of the square matrix A is minus lambda q plus 5 lambda square plus minus 6 lambda plus 5. And so the characteristic equation of the square matrix A is lambda q minus 5 lambda square plus 6 lambda minus 5 is equal to 0. Now step 2. You know that every square matrix satisfies its Caley-Hamilton theorem, its own characteristic equation by Caley-Hamilton theorem. So a cube minus 5a square plus 6a minus 5, here I3 is equal to 0. Here 0 is the 3 by 3 0 matrix. Now to verify the Caley-Hamilton theorem, first find a cube. To find a cube, first find a square. A square is a into a. Now putting the values of a into a, we get the product of these two matrices. We get the 2 by 2, 3 by 3 matrix is minus 2, 1, 4, 3, 1, 3, and last row is minus 5, 5, 40. Now a cube equal to a square into a. I'm putting the values a square and a, and product the a square and a, we get a cube is minus 5, 5, 14, minus 3, 4, 15, and last row is minus 13, 19, 51. Now from the left hand side of this equation, that is a cube minus 5a square plus 6a minus 5i, we get. Now putting the values of a cube, a square, a and I3, and after calculation we get the 3 by 3 0 matrix. From this it is clear that the square matrix A satisfies its characteristic equation. Therefore Caley-Hamilton theorem is verified. Here another example. If A is a 3 by 3 matrix and the matrix is 1 0 2 0 minus 1 1 0 1 0, then verify that A satisfies its Caley-Hamilton theorem, and hence find A inverse and A to the power 9. To verify Caley-Hamilton theorem, we have to first find the characteristic polynomial and characteristic equation of a square matrix A. We know that the characteristic equation of a square matrix A is determinant of A minus lambda I3 is 0. Now putting the values of A and I3 and taking the determinant of there, we get the characteristic equation of A is lambda q minus 2 lambda plus 1 is equal to 0. Here lambda is the eigenvalue corresponding to the square matrix A. Now we verify we shall verify whether a cube minus 2a plus I is 0 or not. To verify this, first find a cube, a square and I3. Now a square is a into a, and which is equal to 1, 2, 2, 0, 2 minus 1, 0 minus 1, 1. Now a cube is equal to a square into a, and after calculation we get 3 by 3 matrix, which is equal to 1, 0, 4, 0 minus 3, 2, 0, 2 minus 1. So a cube minus 2a plus I is equal to, now putting all the values of a cube, a and I3, we get 0 matrix of order 3 by 3. Therefore, the square matrix A satisfies its characteristic equation. That is Caley-Hamilton theorem verified. Next, now we have to try to find out A inverse. We know that A inverse, definition of A inverse is adjoint A by determinant A. But using Caley-Hamilton theorem, we can also find A inverse. To find A inverse, we use this equation, a cube minus 2a plus I equal to 0. Now, a cube minus 2a is minus I, and here a comma a is common, so a into 2a minus a square equal to I. Therefore, a inverse is 2a minus 2I minus a square. Now, putting the values a I3 and a square, we get a inverse is 1 minus 2 minus 2, 0, 0, 1 and 0, 1, 1. Therefore, by using Caley-Hamilton theorem, we can easily find the inverse of a square matrix. Next, we have to find the a to the power 9. We know that from equation 1, a cube is equal to 2a minus I. Then now cubing both sides, we get it. Left hand side is a to the power 9 and right hand side is 2a minus I whole cube. This is the a minus b whole cube, and a minus b whole cube means a cube minus 3a square b plus 3ab square minus b cube. And applying this formula, we get a to the power 9 is equal to 8a cube minus 12a square plus 6a minus I. Also, we know that a cube is 2a minus I. Now, putting these values, we get a to the power 9 is equal to 22a minus 9i minus 12a square. Now, putting the values of a square, a and I3, we get a to the power 9 is equal to 1 minus 24, 20, 0 minus 55, 34, and last row is 0, 34 minus 21. Thank you.